Welcome back. We're just going over how this might look when you are dealing with applications. Is it different? Is it the same? Does it make a big difference? So obviously we have to learn to do our communication about this through a number of different areas. So it shouldn't matter. The math shouldn't be any different. So when we think about an application, it's the application of a scientific principle. An application of a scientific principle. So we don't want to get too caught up in the idea that somehow we're moving away from the mathematical sciences. Okay, the mathematical sciences, I've gone some way to help you understand, are incredibly helpful when they're understood well. Okay, so when we go to an application of a scientific principle, the scientific principle does not change. So it doesn't matter which one you're in, which viewport, which example you're in. You can do calculus here, you can do it over there. That's the whole idea. So there's no change in that. So let's have a look at the context. The only thing that changes is the context, okay? So the context in this case is the physics. So we talk about the velocity. In everyday life we understand that to be a speed, but there's a difference in the meaning. What's the difference in the meaning? The speed just is a number, isn't it? But the velocity is going to have a direction. All the way from 0 to 80 kilometres per hour. What is the instantaneous velocity? Okay, it's what you read on your speedo. The speedo is measuring the average velocity but measured over quite a short time. So it's a small increment. It's like an update and you don't see it, update, you don't see it, update, you don't see it. In fact, our eyes work that way. I'll leave that for another episode. So average velocity within a time frame is where h is greater than 0, and the increase of t and st is the car's displacement. So all of that, blue, blue, blue. So what has car's displacement, s as a function of t, got to do with velocity? Very good. What has a car's displacement got to do with velocity? Very good. So you do some basic graphs when you go into physics, and they're often not what you're used to. So the average speed, the average velocity, is the distance travelled over the time that you spent travelling that distance. Over the time you spent, or if you like, an interval, a time interval. Okay. So if we would put that on a simple number line, you'd start off at some time, and you'd go along a certain distance, and then there'd be some time plus h, in the event that was a time interval. So there's our interval. So I'm wondering, okay, so let's keep looking. So if we take our function of displacement, our time function, it's like that graph where we took the graph going, remember this, f of x plus h. Oh, f of x. Now we're going to do it differently. We're going to do s of t plus h. Minus s of t, that's our rise. And our run is h. I'm not going to minus the t, so I did for that one. Is that all we're doing? So we're in effect getting a speedo. reading. Okay, speed of reading. What about our instantaneous velocity? Ooh, VT. What's that got to do with anything? And how does it differ from average velocity? Well, we can work this out by having some points on the curve. Here, we're going to... Oh, why is there an insurance policy? Aha! So this must be the conversion of an average, if you like, to a differential. And that is equal to exactly that, the differential of the displacement. So there's your first link in physics. You probably already had it, but velocity, another way of expressing velocity, is to differentiate the displacement. Okay. To differentiate the displacement, and that'll give us velocity. So if I take displacement and ddt, I will get velocity. I wonder what happens if I differentiate velocity. Ooh, velocity with respect to time. Maybe I'll get acceleration. How do I go backwards? Given problems, how do I go backwards? So this is a very common tree that you traverse as you go through your physics. Okay, so often the relationships aren't obvious, but it takes a little bit of weeding through, and then you can work that out. So there'll be some examples for us to follow in that. But that's enough at this point. We just wanted to establish that there was this notion of instantaneous velocity applying to the differential increments of change in either one of the variables, in the same way that we did to find the tangent. So the displacement curve can have a tangent, and that tangent is velocity. Wow. In other words, the m value at the particular point represents the velocity. Great. Okay. Let's just pause on that, see if we can take this context elsewhere. Another context we could consider is the context of electric charge. We can work out the average charge. Now, it's a relationship that is charge Q that's being moved a certain distance. So there's our upper rise and our lower function. Our function, Qt, same thing. Qt plus H, Q of T. So that's our rise. Okay. And our run will be the change between T and T, just like we did when we did our first principles development. So they'll cancel, and we'll be left with H. Now, provided H is not 0, this will help us compute the average. Okay, but what about if we do it over a very small increment of time, delta x? What will that give us? Well, our insurance policy comes in, and as H gets smaller and smaller and smaller, we effectively say that for all intents and purposes it takes on 0, and where we are is actually the gradient at that point. There you go. So again, see if you can interpret this. The differential of the charge is current. Differential of the charge is current. I wonder what that would look like if you did your charge, then did your dq/dt. What are we told we're getting? I is a function of t. What about if you kept going? What if you did the differential of current? Where would that lead you? So once you get the hang of these interrelationships, it's a bit easier for you to understand that these are just based on differentiating one element. Transforms your thinking, doesn't it? Transforms your thinking. All right, economics? Really? You do that with economics? I don't see why not. Okay, so the cost of producing items is given by Cn, number of items. So C, production cost. Okay. MC shows how much the cost changes in a 1 unit change of produced items. So if we take your insurance policy, as N approaches, so this is a slightly different measure of this movement along the quantity. N's the quantity, obviously. And so we've got the cost for the upper value of N and the cost for the lower value of N divided by the distance. So as these things change on this curve, wow, we're able to get a sense of the differential being applied. It's the differential of the cost of producing. Wow. So MC is a function of N also. Okay? MC is a function of N also. So the marginal cost is a result of differentiating the production cost. So these relationships exist. Displacement, velocity, charge, current, cost, marginal cost. These relationships exist as a result of differentials. Now, we've never taught this. We didn't teach this in the development, that when you got a function and you differentiated it, that would mean something different. It means the tangent. Well, yes, it does. It means the tangent at the point. The tangent at the point. And up on physics, the tangent at the point. That part's not changing at all. Okay, very good. What other contexts can we look at? Wow. The context of chemistry. Really? Does that mean that when there's a reaction from materials and their reactants, and the two molecules of water are formed, 2 lots of H2O, there's H2O, the concentration or the number of moles per litre is changing over time as the reaction progresses. The average rate of reaction, and the change of concentration, there you go. Change of concentration is a function of time. So the average time is the change in concentration at the beginning or the end. That's the rise. That's the rise. And the run is H. So that's the same thing. Whatever our curve is, f of x plus h. Everywhere there's a t, you add an h. So we've heard that before. Somewhere along there, that represents the rise. The h represents the run. Somewhere there, we join them together. They get very close. Well, this is the case, isn't it? Rate reaction as a function of time. So we use our insurance policy to show the change of concentration over H is the differential. The differential. Wow. So the reaction rate, the rate of the reaction, is the differential of the concentration. Wow. So there'll be different points in the concentration curve that gives us different reaction rates. That makes sense, doesn't it? Different points along the curve will give us different tangents, different slopes. So we're just using slopes. Okay, different points will get different tangents. We'll get these guys happening. Okay, at different points along the curve. But the basic idea is still the same. Okay. Ooh, biology now. This is the context. Biology is the idea that the number of bacteria changes over time. How? How does it change over time? So the average rate changes in the same way. T starts off at some point and goes along to T plus N at some point along the graph. Okay. So the average rate is the number at T plus H, that's our rise, over our run. That's our average. So for our rate of growth, our instantaneous rate of growth, our average rate of growth is there. Our instantaneous, we use our insurance policy, just like we did before. And we've got our rise and our run. That means at some point we can put the H down to a very small value. And look at that, it's the differential of N. So the rate of growth is the differential of N. Sometimes it's expressed this way, isn't it? It's the differential. So finding those and making them work in different contexts is shouldn't be as daunting as you may have thought. Change of pronumerals and the science, the mathematical science remains the same. That's very, very important. Okay. Ooh, so there we've got an example that requires us to do a bit of work. What is it about the charge in a resistor? What did we learn about that? Is it any surprise that we're talking about charge? If we differentiate charge, what do we get? We get current. So is it any surprise that the first part of the question says, tell us the instantaneous current through the resistor? Oh, they're related, aren't they? The differential of charge is in fact current. So we'll put that relationship at the top. The current can be defined as the differential of the charge. So the differential of the charge with respect to T, the 3 is going to come out the front times 3 T, and we're going to take 3 minus 1 will be 2. Then the next thing is we'll do this. The 1 will come out the front, so we'll leave that one. But the 1 will become a 0. T to the power 0 is simply 1. So it stays as a number. Okay? So 3 8s are 24. So 3.24 T squared minus 3.82. That's the current that flows. Here it is. The differential of the charge. Wow. Okay, amperes. All right. What about the instantaneous voltage across the resistor? So if we have a charge supply, okay, there's our charge supply, current source, and we get a charge, Q, and it goes through our resistor. Here's our resistor. Comes back to our current source. And the question is asking, what's the voltage? What's the voltage that sits there as that current flows, as that charge over time, that differentiated charge flows through as current? I better put that as Q. I'm going to leave it as QT, but I'll put the differential just to remind ourselves that it's the differential. There you go, expressed as a current. QT. Okay, so this is our charge. This is the one that we want here. So our voltage, we know by Ohm's law, the voltage is the resistance times the current. So we've got a 2.85 ohm resistor, and we've worked out our current as 3.24t squared minus 3.82. So we better group that because it's got an algebraic plus minus happening. Okay. And so what's the voltage there? Come on, that's not a big one. Let's get my calculator over. See if we can't do it there. So we're looking at a general form. It didn't specify a particular time that it wanted to know this. Where's t? There's no t. So that's it. That's all it wanted. A general form. Okay, so that's our result in terms of t. So we need to define a t in order to get our voltage drop. Okay, that's the equation for the instantaneous voltage. Now what about the power? So the power will be the voltage multiplied by the current. You can see what's going to happen. 2.85 times this one times this one, which is already that one. Oh, squaring. That's a squaring. So yes, it's voltage times current, but it's also I squared R, which means times 2.85. So that's a bit of fun. Okay? A bit of fun for us to understand that. So really, you should be quite relaxed with the whole process. Okay? The whole process of changing contexts. That's the exciting way to view the world, through the lens of a changing context. Okay? That's the beauty of it. So what have we got here? Let's have a look. Our height function, then the object's initial velocity is given by its velocity, which is the differential of the displacement. So this is our displacement function. Then the velocity is the differential. Oh, look at this. The acceleration is the differential of the displacement in the second degree. I could also write that as the velocity differentiated. I think I did that earlier. Okay? So there's a relationship between displacement, velocity, acceleration, the differentials of one another. Okay? So a very interesting idea there. So we can keep on doing derivatives. I think I covered that, doing higher derivatives. So that's important too. All right, let's see if we can't find a couple of examples for us to do. The position of a moving particle in a straight line. Is given by S equals 20 plus 0.3 t meters. So that's a displacement equation. That's S as a function of t. Okay. Find the velocity. So how do we do that? Well, velocity as a function of time is the derivative of displacement. So all we need to do is to do this displacement with respect to t, and remember this is a function of time, not meters, so be careful with that. Okay, so st is equal to 20 plus 0.3 t. The differential of this is the velocity, which is, what are we going to get? The constant disappears, and you're left with 0.3. So the velocity is 0.3 meters per second. Okay, so it's a constant. Doesn't matter if it's 15 or 20. Doesn't matter if it's the first second. Where's the t? There isn't any. What about if it's the 5th second? Doesn't matter. It's still constant. 0.3 meters per second. What about at 10 or 15? Doesn't matter. It's still 0.3 in this particular example. Okay? The speed is constant regardless of time. Okay, 0.3 meters per second. Because we don't differentiate speed, we differentiate the displacement function. Displacement function is going to be constant. Because the differential of the velocity removes the t. Okay, it removes the t. So the displacement, the moving, will change with time. But once we establish the velocity, it won't be changing. Okay, so that the derivation of that function has implications. Okay, so we need to keep that in mind as we go through those. All right, so I might come back and finish this off and do the last couple of questions as we go. I've got some extra examples there to do as well. We'll be back soon.